Consider the diagram below, where charges are packed closely together to form parallel plates of opposite charge. Let's suppose that the potential difference between the plates is 7 volts, and the equipotential curves that are drawn are at 1 volt intervals. Assume 2 test charges are to be released at the positively charged plate. One of them moves along the path A through H, and the other moves along path P through W. We want to sketch the paths that the charges follow. So one of our particles follows this path, and the other follows this path. It's common for a negative plate to be designated as 0 volts. And that's what we'll do here. There's going to be a 7 volt difference between the negative and positive plate, though. That puts the positive plate at a potential of 7 volts. Now we want to label all of the equipotentials in between. So this equipotential will be the 1 volt potential. This will be the 2 volt, 3 volts, 4 volts, 5 volts, and as you can see, we're gaining in potential as we get closer to the positive plate. Keep in mind that any point on the 1 volt equipotential is at the same potential. So we could label this the 1 volt, the 2 volt, and the 3 volt. Over here we'll have the 4 volt, 5 volt, and 6 volt. These are V values, potential values. Let's find the delta V for a proton going from point A to point H. When it comes to finding potential values, it doesn't matter what type of particle we're dealing with. What matters is the location in the field. And so, at point A, we're at a potential of 7 volts. At point H, we're touching the negative plate, so we're at a potential of 0 volts. The change in potential, therefore, will be V final minus V initial, which is 0 volts minus 7 volts. This is a loss of 7 volts. This is called a potential difference. A potential difference is given the symbol delta V, and potential differences can be either positive or negative. In this case, the proton undergoes a potential drop, or a decrease of 7 volts, as it moves from A to H. Now let's find the potential difference for a proton going from point P to point W. At point P, we're touching the positive plate, so that's a 7 volt potential. At point W, we're touching the negative plate, so we're at a 0 volt potential. Once again, the potential difference is going to be the final minus the initial, which is a 7 volt drop. Same as above. it doesn't really matter what path you take when it comes to your potential difference. And not only that, it doesn't even matter what kind of particle it is. Notice that being a proton never figured into the calculation. It's all about the difference between your final and initial potential. So, if we are to find the delta V for an electron going from A to H, the calculation would not change. -7 volts. For an electron taking the path P to W, the delta V will be -7 volts. Those were potential difference values. Now let's find a change in potential energy. That's a little bit different. We want to do it first for a proton going from A to H. Now the relationship between a change in electric potential energy and a potential difference is this. We want to multiply the charge of the particle that's moving in the field times the potential difference to get the change in potential energy. Now for a proton, our charge will be 1.6 times 10 to the minus 19 coulombs. We'll multiply by a -7 volt potential difference. I get -1.12 times 10 to the minus 18 joules. It should make sense that a proton traveling along this path will lose potential energy. Why? Because it has the most electric potential energy when it's near the positive plate. Because the positive plate's field can push the proton away from itself. But when the positive charge is near the negative plate, that's when we have the least electric potential energy. So the change is definitely negative. Now let's find the change in electric potential energy for an electron, which takes path P to W. Alright, so when an electron is near a positive plate, the electric field can't do any work on that particle. So we're going to find that this is a place where it has the least electric potential energy. If, on the other hand, that electron were near the negative plate, then it would really be pushed away from the negative plate by the field. And so we're going to find that it would have the most electric potential energy at that point. So the situation is reversed when we're discussing protons versus electrons. However, the formula is still the same. Charge on an electron is -1.6 times 10 to the minus 19. Our delta V in going from P to W will be -7 volts. So if an electron is to be pushed from the left side to the right side, that's going to be a gain of 1.2 times 10 to the -18 joules. What if a proton is to be moved from point H to point P? Go ahead and calculate the change in electric potential energy for yourself, and then I'll give my answer. Okay, so our formula will be the same as before. We'll use the charge on a proton. And when it comes to the delta V this time, we're going from negative plate to positive plate. We're going from a 0-volt potential up to a 7-volt potential. So we're going to need a positive 7 volts here for our delta V. In this case, the proton will gain electric potential energy. What about an electron moving from point T up to point C? Go ahead and calculate that one. The electron's charge is negative 1.6 times 10 to the minus 19. We have to calculate our delta V. So we see that point T is on the 3-volt equipotential and point C is on the 5-volt equipotential. So we can do a difference of those potential values and then multiply.